There's a mountain in Alaska that scientists are quietly watching very, very closely. Not because it's cracking apart dramatically on live TV, but because it's moving. Slowly, a few inches at a time. Right above a narrow fjord filled with freezing seawater. And honestly, that's the part that scares researchers the most. Because if this entire slope gives way, it won't just trigger a landslide. It could trigger a mega-tsunami. The kind most people don't even realize is possible. We're talking about a wall of water potentially taller than skyscrapers. Inside Alaska, this has happened before. Back in 1958, a massive chunk of mountain collapsed into a remote Alaskan bay called Lituya Bay. The impact created the largest tsunami ever recorded in human history. The wave ripped up mountainsides more than 1,700 feet above sea level. Think about that for a second. That's taller than the Empire State Building. Trees were stripped completely off the cliffs. Entire sections of forest vanished in seconds. And now, scientists are worried another version of that disaster could happen again. Because deep inside Prince William Sound, near Barry Arm Fjord, an enormous mountainside is becoming unstable as glaciers melt away around it. For thousands of years, ice held the slope in place. Now, the ice is disappearing, and the mountain is adjusting to the pressure change in real time. Satellite radar has detected movement across a huge section of the slope. Cracks are spreading. The whole thing is slowly creeping toward the water below. At first, researchers thought the movement might stabilize, but over time, the data kept coming back with the same message. The mountain is still moving. And Alaska is one of the worst possible places for this kind of instability. The region gets earthquakes constantly. If strong shaking hits an already weakened slope above a confined fjord, the results could be catastrophic. That's because fjords work almost like giant funnels. When huge amounts of rock slam into deep, narrow water, the energy has nowhere to go except outward and upward. That's how mega-tsunamis are born. Not from the open ocean, from entire mountains suddenly collapsing into the sea. And here's the creepy part. Scientists believe climate change may be increasing the risk. As glaciers retreat across Alaska, they're removing the ice that once supported steep mountain walls. Slopes that stayed frozen and stable for thousands of years are now starting to deform. Most tourists cruising through Alaska's fjords have no idea this threat exists. They see glaciers, whales, calm water, silent mountains. But the landscape is changing faster than it looks. Because underneath all that beauty, the geology is starting to move. And somewhere in the cold darkness above Barry Arm Fjord, an entire mountainside is still inching toward the ocean. Scientists are watching it carefully. Because if it finally breaks loose, there may only be minutes before the water explodes upward. If you fly over Barry Arm Fjord today, nothing immediately looks wrong. That's what makes this whole thing so unsettling. Huge glaciers still cling to the valleys around Prince William Sound, like they've been there forever. And in a way, they have. Some of this ice formed long before human civilization even existed. But over the last few decades, the landscape has started changing fast. Really fast. The Barry Glacier has been retreating deeper and deeper into the mountains, pulling away from the fjord year after year. And as the ice disappeared, scientists started noticing something strange high above the shoreline. An entire mountainside was beginning to deform. At first, the movement was tiny, barely measurable, but modern satellites can detect changes smaller than the width of a finger from hundreds of miles above Earth. And the satellite data coming back from Barry Arm started making geologists nervous. Because the slope wasn't stable. It was creeping downhill, almost like the mountain itself was sagging toward the water. Researchers eventually identified a gigantic, unstable mass of fractured rock sitting above the fjord. The collapse zone stretched across an area so large, it was difficult to fully understand from ground level. Some scientists compared it to an entire section of mountain beginning to detach. And the craziest part? The glacier may have been the only thing holding it together. For thousands of years, thick ice pressed against the base of the slope, like a giant frozen support wall. Geologists call this buttressing. The glacier basically acted like structural reinforcement for the mountain. But now the ice is melting away. And once that support disappears, gravity starts taking over. This process has a weirdly simple name. Basically, the mountain loses the thing that was helping keep it stable. Then cracks widen, pressure redistributes, rock starts shifting, and eventually, in some cases, entire slopes fail. Scientists have seen smaller versions of this happen in glacial regions around the world. But Barry Arm stands out because of the scale. The unstable slope sits directly above deep, confined water. That combination is dangerous, because if the mountain collapses onto dry land, it's a landslide. If it collapses into a fjord, it becomes something else entirely. The water gets displaced instantly. Millions of tons of rock slam into the inlet. The fjord basically explodes. And unlike normal tsunamis that travel across oceans for hours, landslide tsunamis happen almost immediately. There's barely time to react. One minute, the water looks calm. The next minute, a wall of ocean is racing through the fjord. Scientists started modeling different collapse scenarios at Barry Arm, and some of the simulations were honestly terrifying. Depending on how much rock fails and how fast it enters the water, the resulting wave could be enormous near the impact zone. Some projections showed catastrophic flooding potential throughout parts of Prince William Sound. And here's where things get even worse. Alaska gets earthquakes constantly. Southern Alaska sits near the boundary of the Pacific Plate and the North American Plate, one of the most active tectonic zones on Earth. The ground shakes there all the time. Most quakes are small, but not all of them. If a major earthquake hits while the slope is already weakened, that shaking could potentially trigger sudden collapse. And scientists can't say exactly when or if that might happen. That uncertainty is what keeps this situation so uncomfortable, because mountains don't always fail gradually. Sometimes they sit there for years, looking mostly stable. Then one day, everything gives way at once. Researchers monitoring Barry Arm have noticed that different sections of the slope move at different speeds, depending on temperature, rainfall, snowmelt, and seasonal conditions. Freeze-thaw cycles slowly pry the rock apart from the inside, and climate change is accelerating almost every one of those processes. That's the bigger story here. This isn't just about one mountain. It's about an entire Arctic system changing faster than expected. As glaciers retreat across Alaska, they're exposing slopes that haven't been ice-free for thousands of years. Mountains are suddenly being forced to readjust to conditions they were never meant to experience this quickly. And scientists are starting to realize something kind of disturbing. Barry Arm may not be unique. There could be other unstable slopes developing across Alaska right now that nobody has fully identified yet. Because these regions are huge, a lot of the terrain is barely monitored at all. Some fjords are accessible only by boat or helicopter, meaning instability can develop silently for years before anyone notices. And honestly, that may be the creepiest part of all. Not the cracks scientists already know about, but the ones they haven't found yet. When scientists talk about mega-tsunamis in Alaska, they're not talking about some hypothetical future disaster. They're talking about something that already happened. And honestly, the story still sounds unbelievable even today. July 9th, 1958, southeastern Alaska, Lituya Bay. At the time, almost nobody outside the region had even heard of the place. It was remote, wild, surrounded by steep glacial mountains and deep icy water. Beautiful country, but dangerous country. That evening, a massive earthquake struck along the Fairweather Fault, magnitude 7.8. The shaking tore through the mountains around the bay with incredible force. Entire cliffs started collapsing almost instantly. Then one section of mountain gave way completely. Around 40 million cubic yards of rock and ice broke loose from high above the inlet and crashed directly into the water below. And when it hit the bay, the ocean detonated. That's really the only way to describe it. The impact displaced so much water, so violently, that a gigantic wall of ocean shot upward through the narrow fjord. The wave climbed the mountainside surrounding Lituya Bay, higher than anyone thought physically possible. 1,720 feet above sea level, more than 500 meters. To put that into perspective, that's taller than the Empire State Building, taller than most skyscrapers on Earth. The force ripped every tree off the surrounding cliffs. Entire forests vanished in seconds, leaving giant scars on the mountainsides that are still visible decades later. And the craziest part? The wave itself didn't travel across the Pacific like a normal tsunami. Most of the destruction happened right there, inside the confined bay. That's what makes mega-tsunamis so terrifying. They're local, sudden, explosively violent. People nearby don't get hours to evacuate. Sometimes they barely get seconds. A few fishing boats happened to be inside Lituya Bay that evening. One crew later described hearing what sounded like an explosion deep inside the mountains. Then they saw the water rising. Fast. Way too fast. One boat somehow survived after being lifted over a forested spit of land and carried back into the bay. Another disappeared completely. 2 people died. And honestly, the death toll could have been far worse. The only reason the disaster wasn't catastrophic on a larger scale was because almost nobody lived there. That's something scientists keep repeating today. Lituya Bay was remote. Barry Arm is not exactly crowded either, but Prince William Sound sees far more activity now than Alaska's fjords did in the 1950s. Tour boats move through the region. Fishing vessels operate there. Cruise ships pass nearby during tourist season. Kayakers explore the coastline. Researchers monitor glaciers throughout the area. Human presence in Alaska's fjords has increased dramatically over the decades, which means the consequences of another giant landslide tsunami could look very different today. And researchers studying Barry Arm know this history extremely well, because Lituya Bay proved something important. Mega-tsunamis are real. Not movie science, not internet myths, real physics. If enough rock collapses into confined water at high speed, the resulting wave can become unimaginably large. And Alaska's geography creates ideal conditions for exactly that kind of disaster. Steep mountains, deep fjords, active earthquakes, rapid glacier retreat, unstable slopes. Everything is there. The ingredients already exist. That's why scientists started re-examining glacial fjords across Alaska after major landslide events in recent years. And what they found was unsettling. As glaciers retreat, many mountainsides are becoming less stable, not just 1 or 2, potentially dozens, maybe more. Researchers began identifying fresh fracture zones high above fjords where thick ice had recently disappeared. Some slopes showed clear evidence of movement. Others revealed giant cracks opening across mountain faces. A few already failed. In 2015, another massive landslide struck Ton Fjord in southern Alaska after glacier retreat destabilized nearby terrain. The collapse generated a huge tsunami wave that tore through the fjord and stripped vegetation from surrounding shorelines. Again, another giant wall of water. Again, triggered by collapsing mountain rock. Again, linked to glacial retreat. Luckily, almost nobody was there. But scientists noticed a disturbing pattern emerging. The warming Arctic wasn't just melting ice. It was changing the physical stability of entire mountain systems. For thousands of years, glaciers acted like frozen structural supports across Alaska's coastal terrain. As those glaciers disappear, the mountains are being forced to readjust incredibly fast. And geology doesn't always adjust gently. Sometimes pressure builds quietly for years, then releases all at once. That's the thing people misunderstand about landscapes like Alaska. They look ancient, permanent, solid, but they're actually moving all the time. Rock shifts, ice flows, fault lines build stress, gravity pulls continuously downward. Most of the time, these forces balance each other out. But when one part of the system changes too quickly, especially the ice, the whole balance starts getting weird. That's what scientists think may be happening now. The glaciers are retreating faster than the mountains can adapt. And in places like Barry Arm, researchers are basically watching a giant natural stress test unfold in real time. Because the slope above the fjord hasn't collapsed. Not yet. But Alaska has already shown the world exactly what happens when one finally does. Nobody knows exactly when a slope like Barry Arm could fail. That's part of the nightmare. Scientists can measure movement, track deformation, monitor cracks. But predicting the exact moment a mountain collapses, that's incredibly difficult. Because gravity works quietly, until suddenly it doesn't. So let's imagine the scenario researchers hope never happens. A late summer afternoon in Prince William Sound. Cold air, low clouds hanging over the fjords, tour boats moving through the water, maybe a fishing vessel nearby. Everything looks normal. Then somewhere high above Barry Arm, deep inside the fractured rock, stress reaches a breaking point. Maybe it starts with heavy rainfall, maybe rapid snowmelt. Maybe a small earthquake nobody even notices at first. Or maybe the mountain simply gives up after years of slow movement. At first, the failure might sound like distant thunder, a low cracking noise echoing across the valley. Then the entire slope begins moving, not small rocks, not debris, an entire section of mountain. Millions upon millions of tons of fractured stone, suddenly accelerating downhill under gravity. And once that mass starts moving, there's no stopping it. The rock tears through the landscape at terrifying speed, dragging dirt, ice, and shattered material with it. Trees snap instantly. Dust clouds explode into the air. The sound alone would be unbelievable, like continuous explosions rolling through the fjord. Then the landslide reaches the water, and that's when the real disaster begins. Because the fjord doesn't absorb the impact, it reacts violently. The collapsing mountain slams into deep confined seawater with unimaginable force, displacing huge volumes of water almost instantly. The ocean erupts upward. Near the impact zone, the wave could rise hundreds of feet within seconds, not gradually, instantly. Researchers studying landslide tsunamis say the first moments would be pure chaos. Water surges vertically, shock waves race through the fjord. Air gets compressed between the cliffs and the wave face. Debris launches everywhere. The surface of the water essentially transforms into a moving wall. And unlike earthquake tsunamis that spread across oceans, this happens inside a narrow, confined channel. That's important, because fjords amplify energy. The wave doesn't have room to spread outward normally, so the force becomes concentrated. The water races through the inlet like a battering ram. If boats are nearby, there may be almost no time to escape. A vessel close to the collapse zone could suddenly find itself facing a fast-moving wall of water, filled with rock, ice, trees, and debris. And honestly, even large ships would be vulnerable under the wrong conditions, especially near steep shorelines where reflected waves create chaotic cross-currents. The danger wouldn't end after the first wave either. Mega-tsunamis inside fjords behave unpredictably. Water rebounds off cliffs, secondary surges form. Huge backwash currents drag debris back toward the collapse zone. Entire shorelines can temporarily disappear beneath moving water. In some simulations, waves generated near Barry Arm continue propagating outward through Prince William Sound, potentially affecting areas far beyond the initial collapse site. Would the wave still be 1,700 feet high like Lituya Bay? Probably not. That event was extraordinarily extreme, but it wouldn't need to be. Even a fraction of that size could still be devastating. A 100-foot tsunami is catastrophic. A 200-foot tsunami is catastrophic. Inside confined coastal environments, even much smaller waves become deadly very quickly. And the geography of Alaska makes evacuation incredibly difficult. Many coastal areas have limited road access. Some communities depend entirely on boats or aircraft. Tourists inside remote fjords may have little understanding of the terrain around them. Cell service can disappear completely in some regions. Emergency response times are slow, even under normal conditions. Now imagine all of that during a sudden geological disaster unfolding in minutes. That's why researchers monitoring Barry Arm focus so heavily on early warning systems. The challenge isn't just understanding the mountain, it's understanding how fast everything could happen afterward. Because time is the enemy in a fjord tsunami. The collapse happens first, then the water moves immediately. No long delay, no dramatic countdown, just impact, and then chaos. One of the strangest things about disasters like this is how peaceful everything can look right beforehand. That's something survivors of landslides and tsunamis mention over and over again. The normalcy, birds flying overhead, still water, quiet air. Then suddenly the environment transforms into something violent beyond imagination. And Alaska's fjords already contain all the ingredients needed for that transformation. Steep, unstable terrain, retreating glaciers, deep confined water, earthquake activity, rapid climate-driven change. Scientists studying these systems often describe them as low probability but high consequence events, meaning the collapse might not happen tomorrow, maybe not even this decade. But if it does happen, the consequences could be enormous. And here's the uncomfortable truth. The more glaciers retreat across Alaska, the more these risks may grow. For a long time, scientists treated climate change and geological disasters as mostly separate problems. One was atmospheric, the other was underground. But in places like Alaska, those lines are starting to blur, because warming temperatures aren't just changing the weather anymore, they're changing the mountains themselves. And honestly, that realization caught a lot of researchers off guard. When most people think about climate change, they picture heat waves, wildfires, hurricanes, melting glaciers, rising sea levels. They don't usually picture entire mountains becoming unstable. But that's exactly what scientists are now documenting across parts of the Arctic and high mountain regions around the world. The process starts with ice, a ridiculous amount of ice. Alaska contains some of the largest glacier systems on Earth outside Greenland and Antarctica. For thousands of years, these glaciers acted almost like frozen architecture across the landscape. They carved valleys, compressed slopes, supported cliffs, locked loose rock in place. And they did it for so long that entire mountain systems evolved around the pressure of that ice being there. Now the ice is disappearing. Fast. Some Alaskan glaciers have retreated miles over the last century. Others are thinning so quickly that scientists can measure changes almost year by year using satellite imagery. And once glaciers retreat, the terrain they leave behind starts behaving differently. Think of it like removing support beams from an old building. At first, nothing dramatic happens. The structure still stands. But stress starts redistributing through places that weren't designed to handle it alone. Tiny fractures appear. Pressure shifts. Weak points begin opening. That's basically what's happening across parts of Alaska right now. And there's another layer to this problem people rarely talk about: permafrost. In cold mountain regions, frozen ground acts like natural cement. Ice trapped inside rock fractures helps hold cliffs and steep slopes together. But when temperatures rise, that frozen cement weakens. The rock loses cohesion. Sections of mountain that stayed locked in place for centuries begin loosening from the inside out. Scientists have started documenting more rock falls, slope collapses, and landslides in warming mountain environments across the world. The Alps, the Himalayas, northern Canada, Greenland, Alaska. Different locations, same pattern. As temperatures rise, high mountain terrain becomes less stable. And the scary thing is how quietly it happens. Most instability develops slowly at first. No giant explosions, no dramatic warning signs. Just tiny changes accumulating year after year. Water seeps deeper into fractures. Freeze-thaw cycles widen cracks. Heavy rainfall saturates weakened slopes. Glacial melt changes pressure distribution. Then, eventually, gravity takes over. One reason Barry Arm worries scientists so much is because it combines all these climate-driven stress factors in one place. Retreating glacier? Yes. Fractured mountain slope? Yes. Deep confined water directly below? Yes. Active earthquake zone? Definitely yes. It's almost like the landscape contains every ingredient needed for a worst-case geological chain reaction. And climate change may be speeding the whole process up. Researchers studying Arctic regions increasingly use a phrase that shows up again and again in scientific papers: faster than expected. That phrase matters, because many glacier systems are retreating faster than older climate models predicted. Permafrost degradation is happening faster in some regions. Coastal erosion is accelerating in parts of Alaska as protective sea ice disappears. Entire Arctic systems are changing quickly enough that scientists are struggling to keep up in real time. And geology doesn't like rapid change. Natural systems usually adapt over centuries or thousands of years, not decades. But modern warming is compressing those timescales dramatically. The mountains are being forced to adjust much faster than normal, and some of those adjustments may become violent. One thing researchers emphasize constantly is that climate change does not cause every landslide or tsunami directly. Gravity still causes landslides. Earthquakes still trigger collapses. But warming can increase instability. It loads the dice. It weakens terrain. It creates conditions where failures become more likely. That's the key distinction. Climate change acts like a stress multiplier, and nowhere is that more obvious than the Arctic. The Arctic is warming roughly 4 times faster than the global average in some regions. Winters are changing. Glaciers are shrinking. Frozen ground is thawing. The landscape Alaska was built on is literally transforming beneath the surface. And scientists are starting to realize this transformation may create entirely new categories of geological risk. Not because nature suddenly became more dangerous, but because the balance that existed for thousands of years is disappearing. The ice that stabilized mountains is retreating. The frozen ground that held slopes together is softening. The climate that shaped these landscapes is changing, and the mountains are responding. sometimes slowly, sometimes violently. That's the unsettling thing about Barry Arm. It's not just a mountain problem, it's a signal, a glimpse of what happens when climate systems and geological systems start colliding with each other in real time. And in Alaska, that collision may already be underway. If Alaska were geologically quiet, the Barry Arm situation would still worry scientists. But Alaska isn't quiet, not even close. It's one of the most earthquake-prone places on Earth, and that changes everything. Because an unstable mountain doesn't necessarily collapse on its own. Sometimes it just needs a trigger, a sudden jolt, a violent shake, a few seconds of movement in the wrong direction. And Alaska gets plenty of those. The entire southern coast sits near the boundary where the Pacific plate is grinding beneath the North American plate. That collision zone stores enormous amounts of stress deep underground. Eventually, the stress releases. When it does, Alaska shakes hard, really hard. Since 1900, the state has experienced multiple earthquakes above magnitude 8.0. That's almost hard to comprehend. Most places on Earth never experience earthquakes remotely close to that size. Alaska has experienced several. The most famous happened on March 27, 1964, Good Friday. At first, people thought it was just another earthquake. Then the ground kept moving, and moving, and moving. The shaking lasted more than 4 minutes. Entire neighborhoods in Anchorage collapsed as the ground beneath them liquefied. Roads split apart. Forests tilted sideways. Coastal land suddenly dropped below sea level. But the worst destruction came from the water. Huge sections of unstable coastline failed during the quake, collapsing directly into the ocean. Underwater landslides triggered local tsunamis that hit coastal communities within minutes. In some places, those localized waves were even more destructive than the main Pacific tsunami generated by the earthquake itself. That detail matters, because it shows how dangerous unstable slopes can become during seismic shaking. And Barry Arm sits directly inside earthquake country. Scientists studying the slope know that a major quake in the wrong place at the wrong time could dramatically increase collapse risk. Even moderate shaking might matter if the mountain is already weakened enough. Think about what's happening up there right now. The slope is fractured. Water is infiltrating the rock. Freeze-thaw cycles are widening cracks. The glacier that once supported the mountain is retreating. Gravity is already pulling the whole system downhill. An earthquake could potentially act like the final shove. And earthquakes don't give warnings. That's what makes this so uncomfortable. A slope failure caused purely by gradual instability might show accelerating movement beforehand. Scientists could potentially detect changes developing over time. But seismic triggers are different. A mountain can go from unstable to catastrophic in seconds. That's one reason researchers remain cautious when discussing Barry Arm publicly. They don't want to sound alarmist, but they also know the region's tectonic history is impossible to ignore. Because Alaska's earthquakes aren't rare events. They're part of the landscape. Thousands occur every year. Most are small enough that nobody notices them. But the stress underground never really stops building. And here's the weird part. Climate change may indirectly influence seismic-related hazards too. Not by causing earthquakes directly, but by altering pressure distribution across the crust through massive ice loss. Scientists are still researching this connection, but in some glacial regions, the removal of huge ice masses appears capable of slightly changing stress patterns underground over long timescales. The Earth's crust responds to weight, and Alaska is losing enormous amounts of ice. Again, it's another example of systems overlapping in ways scientists are still trying to fully understand. Climate, geology, hydrology, tectonics. They're not isolated from each other. They interact. And in Alaska, those interactions can become dangerous very quickly. One major concern is timing. Imagine a strong earthquake striking during peak tourist season, when cruise ships and smaller vessels are moving through the fjords. Imagine unstable slopes already saturated from heavy rainfall. Imagine fractures weakened by summer thaw. That combination could turn a geological event into a full-scale disaster scenario incredibly fast. And honestly, some researchers worry people underestimate how fragile steep glacial terrain can become once instability starts spreading. Mountains don't fail neatly. A large collapse can destabilize nearby slopes too. One landslide may trigger another. Rockfalls can continue for hours afterward. Water displaced by the initial collapse may erode additional shoreline sections. The entire fjord system can become chaotic. That's why scientists monitoring Barry Arm aren't just studying one single mountain. They're studying an interconnected environment under stress. And stress changes behavior, especially in nature. The unsettling reality is that Alaska's landscape is entering conditions humans have never fully observed before. Rapid Arctic warming, accelerated glacier retreat, thawing permafrost. Combined with one of the most tectonically active regions on Earth, that combination is new. And scientists are still learning what it means in real time. But they do know one thing. If a major earthquake hits an already unstable slope above a narrow Alaskan fjord, things could go bad unbelievably fast. One of the strangest parts of the Barry Arm story is this. Scientists are literally watching the mountain move in real time, from space. Every few days, satellites pass over Prince William Sound collecting radar data from the surface below. Those radar signals can detect tiny shifts in terrain, movements so small no human standing there would ever notice them. Millimeters, centimeters, slow deformation across entire slopes. And that technology has completely changed how researchers study unstable landscapes. Years ago, a mountainside like Barry Arm might have remained unnoticed until collapse finally happened. Now scientists can track the movement almost like doctors monitoring a patient. And honestly, sometimes the data looks unsettling. Different sections of the slope move at different speeds. Some areas appear relatively stable for months. Others suddenly accelerate after warm periods or heavy rainfall. The mountain behaves less like a solid object and more like a stressed system, constantly adjusting itself. That's important, because mountains are not actually solid in the way most people imagine, especially glacial mountains. They're fractured, layered, broken internally by millions of years of pressure, freezing, thawing, and tectonic stress. The only reason many steep slopes remain standing at all is because the forces acting on them stay balanced. Once that balance changes, weird things start happening. At Barry Arm, researchers identified giant cracks opening across sections of the slope. Some fractures stretch hundreds of feet across the terrain. Entire blocks of rock appear to be slowly rotating outward, like pieces of the mountain are beginning to detach. And yet, the collapse still hasn't happened. That uncertainty frustrates scientists constantly, because geology rarely follows clean timelines. A slope can remain unstable for years without catastrophic failure, then suddenly collapse in a matter of seconds. Or it may partially stabilize for a while before